Hello dear students of plus one medical and non-medical respected teachers. So today I am going to discuss another important topic, satellites, principle, launching and process of launching a satellite and its orbital velocity from the chapter gravitation of plus one physics. So let us start. First of all, what are satellites? Now, any light body revolving around a comparatively heavy body is known as its satellite. Satellites are of two types, natural satellites and artificial satellites. Natural satellites means God-made satellites, like moon is natural satellite of earth. All planets are revolving around the sun, so these are natural satellites of sun. All planets have different satellites. Jupiter, Saturn, they have so many satellites revolving around them. So, to find, to understand the principle of launching a satellite. So, suppose this is our Earth and we have a tower AB at the surface of Earth. To understand at height of about 300 kilometers. So, what we see when you project a body with some initial velocity, it follows parabolic path and strikes the surface of Earth at point C say. When we increase the velocity of projection, then it again follows parabolic path but strikes at larger distance from the foot of the tower, that is at point D. So it means if you go on increasing the speed, it follows parabolic path and strikes at larger distance from the foot of tower. And a stage comes at a particular velocity when the body strikes just at point D, at point E, which is just diametrically opposite to the tower AB. And if the velocity of projection is further increased, then it starts revolving around the Earth with an orbital velocity V naught. And this orbit of Earth, our orbit is known as parking orbit, in which satellites revolves around the Earth. The velocity of the satellite with which Earth revolves, satellite revolves, is called orbital velocity. So this is how we can understand the principle of launching a satellite at a height of about 300 km. The orbital velocity is 8.1 km per second. Then process of launching a satellite. To launch a satellite, we make use of multi-stage rocket, or in this I will take three-stage rocket to explain the launching of satellite. And suppose this is a rocket which has three stages, 1, 2, 3, and satellite is put at the nose of the rocket. S. No. When the rocket is ignited from surface of Earth, at this point, the fuel inside the first stage starts burning. As a result, it experiences an upthrust in accordance with law of conservation of linear momentum, and satellite rises to height of about 50 km. This first stage takes a satellite to height of 50 km. It is quite big because it has taken the whole rocket along with the satellite through a dense atmosphere. The first stage takes the satellite and the rocket to a height of about 50 km, then it burns off. At this point, the satellite and rocket is tilted a little from the ground remote control. Then again, second stage starts working and it rises and its velocity increases. So this second stage takes the satellite to height of about 150 km. Again, at this stage, the rocket is tilted a little from the ground remote control and then third stage starts working and which takes the satellite to height of about 300 km. Then again the satellite which was put at the nose of the rocket, when third stage drops off, its satellite is tilted a little and then it starts revolving around the earth in a particular orbit. The velocity required to put this satellite into its orbit is called orbital velocity. So at height about 300 km, the orbital velocity is about 8.1 km per second, which is less than escape velocity of Earth, which is 11.2 km per second. So this is how satellite is made to revolve in a particular orbit. Clear? Then expression for orbital velocity. Now, when a satellite revolves around the Earth or a planet, the necessary centripetal force required for this purpose is provided by the gravitational force. So it means gravitational force Fg is equal to centripetal force Fc. Therefore, Gmm upon r square is equal to mv square upon r. Small m cancels, 1r cancels, or v naught comes out to be under root gm by small r. The smaller distance of the orbit from the center, the radius of the orbit of the satellite. If h is the height of satellite from surface of Earth, then small r is equal to capital R plus h. So v naught is equal to under root gm plus over r plus h. So which is required expression for orbital velocity. Now when h is less than r, when satellite is very close to surface of Earth, h is small as compared to radius of Earth, which is chords of kilometer, 6400 km, and h is about 300 km in the near the surface of Earth. So h can be neglected as compared to r, or g is equal to gm upon r square, value of g at surface of Earth. So gm is equal to gr square. We substitute, it will be under root gr square upon r in, that is under root gr. So which is required expression for orbital velocity in terms of acceleration to gravity and radius of Earth. So this is known as expression for orbital velocity. No, escape velocity v is equal to under root 2 gr. Therefore, v is equal to under root 2 times v naught. It means this gives relation between escape velocity and orbital velocity of a satellite. So, escape velocity of a satellite is equal to under root 2 times the orbital velocity of the satellite. Now, we can find expression for time period of satellite because it revolves in a circular path. So, it is given by t is equal to circumference 2 pi r plus h radius of orbit over v naught orbital velocity. It will be 2 pi r plus h for under root gm under root r plus h. So, simplifying t is equal to 2 pi r plus h power 3 by 2 under root gm. So, from this expression we can calculate time period of satellite according to height of satellite. Similarly, we can find expression for height of satellite. So from this t square, squaring both sides, 4 pi square upon gm r plus h whole cube, or r plus h is equal to gmt square upon 4 pi square or 1 by 3, or h is equal to gmt square upon 4 pi square power 1 by 3 minus r. So this gives expression for height of a satellite. So height of satellite and time period of satellite or velocity, we can calculate all these things. Then we come to what are geostationary satellites. Those satellites which appear to be stationary or at rest, with respect to surface of Earth. They are known as geostationary satellites. Their location remains fixed. They remain at the particular spot. So that's why these satellites are used as communication satellites because they are located at a particular place. So they are used as communication satellites. We use communication satellites to run our television, mobiles, phones, internet, everything that is taken from the communication satellites. So geosynchronous satellites have time period of 24 hours and height is equal to 36,000 kilometer. We calculate it. Then they are also known as communication satellites. They are used for forecasting weather, Mausam da Hal. They are used in war. Nowadays we all know satellites are used in war. They are used to study atmosphere of Earth. They are used to study exact dimensions of Earth, shape of Earth, and for GPS purpose we use to locate some place when we want to go anywhere. So we use this GPS system, which all are use of geostationary or communication satellites. So there are so many communication satellites revolving, thousands of communication satellites are revolving around the earth by all the countries. They have control over these satellites. So this is all about satellites. So natural satellites, I already told, all planets revolve around the sun. They are natural satellites, man-made satellites. And artificial satellites are human-made satellites, which are all geostationary communication satellites to study forecasting weather during war, all that. The first natural artificial satellite was launched by Russia, Sputnik first in 1957. Aryabhat by India. There are so many satellites. Nowadays, every year we see the launching of new satellites like Chandrayaan. So this is how a satellite is launched and expression for orbital velocity of a satellite. So till next video, stay tuned, be happy, all the best, good luck.